All right. Hey, everybody. So in this video, we are going to introduce one of the big objects here at the end of Calculus 2, the Taylor series. Our goals for this video are to introduce what a Taylor series is and to calculate a handful of examples. So a Taylor series is, in essence, going to combine the two big ideas that we've been discussing recently, that of a power series and that of a Taylor polynomial. And in essence, a Taylor series is going to be the infinite version of what a Taylor polynomial was, as follows. So formal definition is this. A Taylor series centered at the point x equals a is a power series that has a very particular form, right? So as a reminder, every power series had this form right here, the sum as n goes from 0 to infinity of some coefficient, c sub n, times x minus a to the n, right? This was every power series had this form. A Taylor series is a particular power series where the c sub n has a very special form. And I realize what I really, it will be as this, right? So for some function f of x, little f of x, and let's assume that little f of x is differentiable, so we can calculate its first derivative, second derivative, but so on. We can calculate as many derivatives of it as we want. Then our coefficients will be this. They will be the nth derivative of f, evaluated at some point a, divided by n factorial. So this is the same structure that our Taylor polynomials had in our previous set of videos, right? And so what we're doing is we're explicitly saying that c sub n is equal to that expression. C sub n equals nth derivative of f at a divided by n factorial. Okay. So this object will be called a Taylor series. Now, I want to point out, notice, right, when it comes to series, we often would look at a partial sum. So instead of going from n equals 0 to infinity, we would look at a partial sum. N goes from 0 to some capital N, right? So it'd be some finite sum instead of an infinite sum. And in the case of the Taylor series, the partial sums of the Taylor series are just our Taylor polynomials from before, right? So again, our Taylor polynomials would be what would happen if we only calculated this for a finite number of values, while the Taylor series is what we get when we extend this as a sum for n goes from 0 to infinity. Now, a really big idea is this, down here in bold. If our capital F has a power series representation for some radius of convergence, then the power series representation we get is the Taylor series for the function f of x equals capital F of x. In other words, what I have here are sort of two expressions. I have this capital F, which is being used to represent the whole thing, and this is in terms of some function little f of x. What I'm saying here, perhaps too confusingly, is that those two f's are actually one and the same. In other words, if I have a function, capital F of x, and I want to construct a power series representation for it for some radius of convergence, then I can do so using this formula here and by calculating out derivatives of my capital F. So for many functions, we can now compute not only the function itself, but we can compute a Taylor series approximation for that function. All right, let's see an example of this. Oh, I should say, if we center our Taylor series at a equals 0, right, and so that simplifies this formula a little bit, we call the series a Maclaurin series, just like our relationship between Taylor polynomials and Maclaurin polynomials. Okay, so let's look at an example. Let's look at the function f of x equals sine of x, and let's calculate a Taylor series representation for this, or rather a Maclaurin series representation. So we'll focus at a equals 0. So to do this, we need to calculate or figure out a nice pattern for how to calculate the derivatives of this function at, let me actually give myself a little more room, derivatives at n equal, or at a equals 0, right? So we need to calculate f of 0, f prime of 0, f double prime of 0, f triple prime of 0, f to the, the fourth derivative of f at 0, and so on, right? And what we ultimately want is a formula for fn at 0, so the nth derivative of f at 0. And we've done this already in a previous video, so I won't go through all the gory details, but our function at 0 is just 0. The derivative of sine is cosine, and at 0, cosine of 0 is 1. F double prime, that was negative sine, so that's negative 0. F triple prime would be negative 1. The fourth derivative would be 0. And then this will actually repeat, right? So the next one would be a 1, a 0, a negative 1, a 0, and so on, right? And so we actually get this formula where f to the n of 0 is either equal to 0 plus 1 or minus 1, depending on what our formula, or depending on what our n value is. Right, so we could write this as follows. So we could write this as this equals 0 if n is even, or it equals plus or minus 1 if n is odd. Okay, but there's a slight problem in how we've written this, specifically. I mean, first of all, it's just sort of piecewise defined, so that's always a little bit clunkier to use in practice. Secondly, the way I've written this at the moment, sort of saying it's plus or minus 1 if n is odd, that's not precise. I would want to say exactly when it's equal to 1 and exactly when it is not equal to 1. So we're actually going to do something kind of clever here. And then maybe I should say, under this formula, our Maclaurin series would be the sum as n goes from 0 to infinity of that expression, right? So f sub n of 0 divided by n factorial times x to the n. Now, I think what we actually want to do here, though, right, to make this slightly more precise, is we want to be a little clever in how we are indexing these values. Specifically, we recognize that because all of the even values will have a coefficient of 0, we don't actually care about those values, right? What I really care about are the values when n equals 1, n equals 3, n equals 5, 7, 9, and so on, right? And so what I'm actually going to do is I'm going to re-index these so that the, and let me re-index these by a lowercase m, right? So the very first m value that I care about, number 1, that could be my, my value 1 here. The next value that I care about is 3. That could be my second m value, and so on, right? Or actually, because I like to start my indices at 0 in a Taylor series, let me convert this. This will be my 0th entry here. This will be my first entry here. So my second entry will be this one, third entry is this one, fourth entry is this one, and so on. And so if I really want to use these indices, the m values instead of the n values, then I have to recognize that my, to get from n to m, I would see that my, we would have this relationship, right? Where m times 2 plus 1 is equal to n. And so when I talk about the n values that I care about, I'm really talking about these values right here. All right, and now for these values, we can go ahead and figure out which m values are +1 and which m values are -1, right? So this first one, that was the first derivative, right? So that was m equals 0. That was positive. The -1, that was where m was equal to 1, right? I should say this was the third derivative, right? So -1 corresponded to the third derivative. So that was when m was equal to 1. This +1 down here corresponded to when m was equal to 2. This one corresponded to when m was equal to 3. And so what we actually see is that our coefficient, right, the +1, -1, +1, -1, is really just going to be, all of these values are going to be -1 raised to the mth power, right? And so this has this element of an alternating series, or yeah, an alternating sequence at least. So -1 to the m will give me my corresponding +1, -1, +1, -1 that I really want. And so we can now rewrite the series. This is now the sum not as n goes from 0 to infinity, but as m goes from 0 to infinity, right? And by switching over to m's, I'll only be grabbing the odd values of n that we had before. And so that f to the n of 0, right, that nth derivative of f at 0, that just becomes these values, which could be represented as -1 to the m, divided by n factorial, so that becomes 2m plus 1 factorial, times x to the 2m plus 1. All right, and what we have here is a nice formula that represents our sine function, right, under the guise of a Maclaurin series. And this is indeed the Maclaurin series, or the power series, associated with the sine function centered at 0. Awesome. Okay, let's turn to what will ultimately be a slightly easier example. Right, we started with sine because we've had some familiarity with sine in our previous video. Let's look at another example. Let's look at e to the x. And again, we'll calculate the Maclaurin series. So this will be centered at a equals 0. So what we need to do is we need to calculate f at 0, f prime at 0, f double prime at 0, f triple prime at 0, and so on. And we ultimately need a formula for f nth derivative at 0. Now, this turns out to be an easier, I should say, an easier set of calculations to make than for our sine function, because f of 0, that's just e to the 0, right? And e to the 0 is equal to 1. And because of, the fact that we're dealing with e to the x, we actually recognize that the derivative of e to the x is just e to the x. So that's going to be 1. This is going to be 1. This is going to be 1. In fact, all of our derivatives of e to the x at 0 will just equal 1. And that is awesome, right? Right away, this is a much more straightforward problem than the last one. I don't have to do any of that complicated index shifting. I can simply recognize that when it comes time to take my sum as n goes from 0 to infinity of f to the n of 0 over n factorial times x to the n, right? I can just recognize that this piece right here, this numerator, is just going to be always equal to 1. And so what we get as a result is our Maclaurin series for e to the x, the sum as n goes from 0 to infinity of 1 over n factorial times x to the n. And that's awesome. To write out the first few terms, just so we get a sense of what this looks like, the 0th term is just a 1, right? 1 over 1 times x to the 0, plus x over 1, plus x squared over 2, plus x cubed over 3 factorial, so that's 6, plus x to the 4th over 4 factorial, so that's 24, and so on, and so on, and so on. Cool. So that is our Maclaurin series for e to the x. And what we'll see is that this actually converges to the value e, or the function e to the x for any x value. In other words, the radius of convergence in this case is actually equal to infinity. And so this is a true representation of the function e to the x. All right, that's all I got for this video. I'll see you all next time.